This is content of part 10a. If you're interested only in specific part of this video, just jump to its start time. Finally, I would like to give a few of my recommendations for fabrication technology of nanomagnets. The recommendations are based on my personal experience for growth and nanofabrication and measurement of many nanomagnets. The target of the recommendation is improvement of nanomagnet properties for its use in the magnetic random access memory or MRAM in short, and for the sensor applications. The first recommendation is very trivial. Grow your samples with as few contamination as possible. Also get as smooth and sharper interface as possible. Such an interface is very important to enhance the spin-orbit interaction. For example, you may recall that the strongest magnetic field of spin-orbit interaction is often at the top layer at the interface, due to the largest deformation of orbitals of this top layer. In the case of rough interface, or in the case when the change from one material to another material is not step-like, the orbital deformation is small, resulting in a weak spin-orbit interaction. It is not easy to check whether the used fabrication technology complies with the requirement for fabrication of smooth and sharp interface. As you will see later in this video, one atom at the interface may influence magnetic properties of tiny nanomagnet. It's rather hard to check the quality of interface for such severe requirements, for example by using an electron microscope. An important measurement which clarifies the quality of interface for specific fabrication technology is measurement of the coefficient of spin-orbit interaction versus anisotropy field. For the nanomagnet, it gives the information about inhomogeneity of the thickness over the wafer and about the quality of the interface. This graph shows my measurement of coefficient of spin-orbit interactions versus anisotropy field for nanomagnet I have fabricated. Each dot corresponds to one measured nanomagnet. A different color corresponds to a different wafer. The first important parameter of this graph is density of dots, which indicates the homogeneity of growth and the fabrication. The less sparse the dots are, the better homogeneity of nanomagnet thickness and interface the fabrication technology provides. The case when all dots of one color are in one small region means that the thickness and interface quality are nearly the same for all nanomagnets fabricated on different parts of the wafer. When data is sparse over a large region, means there is something wrong with the fabrication technology. It is okay that the data of different wafers are in different parts of graph. It is because both coefficient of spin-orbit interaction and anisotropy field substantially depend on the nanomagnet material, nanomagnet structure, sputtering and annealing conditions, and on features of the nanofabrication. I have tested different fabrication technologies. As a result, even for the same material and structure, there is a good and not so good wafers. You can see both very sparse and very concentrated data for nearly identical wafers. Data of multi-layer nanomagnets are shown by stars. In case of a multi-layer nanomagnet, it's very difficult to keep each next grown interface at the same quality, but it could be possible to sustain the homogeneity for each layer thickness. In the case of such wafers, the dots are relatively sparse, but all dots are close to one straight line like this. The case when all dots are along one line means the wafer is not the best, but relatively good and acceptable. You can find more details about this dependence in this video, part 5b. Another important parameter of nanomagnet, which is important to evaluate, is amplitude of oscillation of anisotropy field. You may recall in previous video I have explained how to measure such an oscillation. These are two graphs of different scale show the oscillation amplitude versus coefficient of spin-orbit interaction. Let's check this one. Also in previous video I already explained why the amplitude of oscillation is proportional to coefficient of spin-orbit interaction. You see? The importance of oscillation is that they are characteristic of quality of the interface without influence of properties of the bulk of the nanomagnet. A larger amplitude of oscillation means that magnetic properties of the nanomagnet are more influenced by the interface and less influenced by the bulk of nanomagnet. A smaller oscillation like this means that the bulk properties dominate. A nanomagnet for which the interface properties dominate are important for a variety of applications, from a sensor to a memory. In case of molecular recognition sensors, for example, a substantial change of magnetic properties is important for event of object touching the interface of nanomagnet. A nanomagnet having the largest oscillation is the first choice for such a sensor. For this data, it is also important that the data from one wafer should not be sparse. Even where the data is sparse, at least the dot should be along a straight line. In this case, even so, the interface qualities varies along the wafer. The layer thickness is rather homogeneous. Another parameter which is important to evaluate is the intrinsic magnetic field. The intrinsic magnetic field is substantially different from wafer to wafer, but there is some common tendency like this. The intrinsic magnetic field influences some important parameters of nanomagnet. For example, threshold current for the magnetization reversal. Yes, it is intrinsic magnetic field. You can check about properties and measurements of internal magnetic field in this video, part 1c. Both the demagnetization field and magnetic field of spin-orbit interactions contributes to internal magnetic field, but their contribution are opposite. The direction of magnetic field of spin-orbit interaction is along internal magnetic field and contribute positively to it. The direction of demagnetization field is opposite to internal magnetic field, and therefore the demagnetization field reduces internal magnetic field. As you can see, internal magnetic field decreases with increase of coefficient of spin-orbit interaction, which means with increase of magnetic field of spin-orbit interaction. It might look inconsistent because the increase of magnetic field of spin-orbit interaction should lead to increase of internal magnetic field. However, the demagnetization field plays an important role in this dependence. The coefficient of spin-orbit interaction increases when the quality of interface becomes better. However, the improvement of interface quality also leads to increase of demagnetization field, but the demagnetization field reduces internal magnetic field. As this experimental measurement shows, a larger reduction of internal magnetic field due to increase of demagnetization field dominates over a small increase of internal magnetic field due to increase of magnetic field of spin-orbit interaction. In nanomagnet, internal magnetic field keeps the magnetization along the magnetic easy axis. The energy splitting between spin-up and spin-down energy levels in nanomagnet is linearly proportional to the internal magnetic field. As a result, both precession frequency and the rate of precession relaxation are proportional to internal magnetic field. As it is explained in this video, the rate of precession relaxation becomes larger when the split between spin-up and spin-down energy levels increases. Therefore, a nanomagnet of smaller internal magnetic field has a slower precession relaxation rate. As you can see, there is a substantial variation of internal magnetic field within one wafer, corresponding to dots of the same color. It's not good. For example, the threshold current for magnetization reversal is proportional to the precession relaxation and therefore to the internal magnetic field. It means that there is an undesirable variation of threshold current along a wafer due to this variation of internal magnetic field. The fabrication technology should be improved to minimize this variation. Next, I will talk about the importance of controlling contamination and film thickness for growth of nanomagnet. For this technology, one atom truly matters. It is not just a slogan. One foreign atom at interface may change substantially the strength of spin-orbit interaction. Addition of one atomic layer changes drastically the properties of nanomagnet. As example, let me show how one atomic layer of thickness substantially influences the properties of iron-boron nanomagnet, which is fabricated by sputtering. The magnetic properties of iron-boron nanomagnet substantially different for tiny change of nanomagnet thickness. In case of nanomagnet thinner than 0.8 nanometer, the nanomagnet is paramagnetic. The reason for paramagnetism is that the film is not continuous, and there are iron-boron islands, which are not connected. Therefore, there is no exchange interaction between these tiny islands, and small thermal fluctuation can easily reverse the magnetization of those separated iron islands. A thicker nanomagnet is ferromagnetic and can be used as a nanomagnet. For thickness in range between 0.8 and 1.6 nanometer, the equilibrium magnetization of nanomagnet is perpendicular to the plane. For a thicker nanomagnet, the equilibrium magnetization becomes in plane. The nanomagnet, which has a perpendicular to plane equilibrium magnetization, is most interesting for a variety of the applications. The critical thickness at which the direction of equilibrium magnetization changes from perpendicular to plane to in plane is called the critical thickness. The critical thickness depends on ferromagnetic material, but it also depends substantially on the quality of interface. The reason why the direction of equilibrium magnetization changes from perpendicular to plane to in plane is following. The electron orbitals on top of the interface are deformed. As a result, they experience a substantial magnetic field of spin-orbit interaction. But the stance of the spin-orbit interaction depends on the magnetization direction. Magnetic field of spin-orbit interaction is large when the magnetization is perpendicular to plane, and it is small when the magnetization is in plane. As a result, the magnetic energy of this top layer is substantially higher when the magnetization is perpendicular to plane, and for this layer it's energetically favorable for the magnetization to be perpendicular to plane. It is in contrast for atoms in the bulk of nanomagnet. The orbital of the bulk atoms are rather symmetrical, and there is almost no spin-orbit interaction for them. For the bulk atoms, it's energetically favorable when the magnetization is in plane. The reason for that is the demagnetization field. In contrast to magnetic field of spin-orbit interaction, which is directed along the magnetization, the direction of demagnetization field is opposite to the magnetization. Similar to magnetic field of spin-orbit interaction, the magnetization field is large when the magnetization is perpendicular to plane and very small when magnetization is in plane. As a result, the magnetization field reduces magnetic energy, and it's energetically favorable for the bulk atom when the magnetization is in plane. For a thinner film, when there is less bulk atoms, the contribution of interface atoms to the magnetic energy becomes dominated, which makes the equilibrium magnetization perpendicular to the plane. For a thicker film, when there are more bulk atoms, the contribution of the bulk atoms to the magnetic energy becomes dominated, which makes the equilibrium magnetization in plane. The critical thickness can be calculated by minimizing the total magnetic energy. The mass is relatively simple, and you can find it here. Thickness dependence, critical thickness, page number 5. The formula for critical thickness is here. The critical thickness depends on the strength of the spin-orbit interaction and the strength of the demagnetization. Since both the strength of spin-orbit interaction and strength of demagnetization are substantially influenced by the interface quality, the critical thickness substantially depends on interface quality as well. This graph shows the calculated magnetic energy of nanomagnet as function of its thickness. A positive energy means the equilibrium magnetization is perpendicular to plane. A negative energy means the equilibrium magnetization is in plane. The energy linearly decreases with increase of thickness. The critical thickness corresponds to point when the line crosses a zero energy line. The solid and dashed lines correspond to calculation for nanomagnet with slightly different quality of interface. As you can see, the critical thickness substantially depends on the quality of interface. I would like to emphasize once more that the magnetic properties of nanomagnet substantially depend on its thickness. A thickness of one atomic layer is roughly equal to 0.1 nanometer. Addition of only one atomic layer may change the equilibrium magnetization from perpendicular to plane to in plane direction, meaning a change of type of nanomagnet. Therefore, precise control of thickness is critical for this technology. If you are interested to see the content and other parts of this video, you can find the links below this video.